after our part concerning the foundations of quantum computing and quantum communication, let us have some philosophical prospects. But actually, from my point of view, the philosophical discussion is much more intellectually ambitious. The mathematical stuff, I think, is rather easy. Philosophical prospects of quantum computing. And here I start with the very beginning of digital computing. And that was Turing. Alan Turing, with his famous paper from 36 and 37, the Turing machine. I only want to highlight here the main concept, the strict separation in his theoretical description of a digital computer, the strict separation between a memory and a processor. In the Turing concept, the memory is described by a tape which is not limited at the end. That means if it is needed, it can be extended. It is not said that you must believe in an unfinite state. What means an unfinite tape? Technically, nonsense. It needs only the assumption that if it is needed, you can extend your memory. You can extend your store. And the tape is here divided in squares, and the squares can be printed by digits. And in the simplest case, these are the binary digits, and you know all kind of information can be represented in this way. And the other part is the processor. And the processor means a technical unit which is able to print, to write, and to manipulate the store. Here, the tape. In principle, that is all. Later on, it turned out that other suggestions of digital computers or of digital algorithms are mathematically equivalent to the Turing machine concept. And therefore, later on, the concept of the Turing machine was distinguished as a general representative concept for a digital algorithm in general. That is, of course, an assumption, and it is called after the author Church's thesis. Another interesting and essential suggestion of Turing was the universal Turing machine. At that time, a theoretical concept. Universal Turing machine, it is a distinguished Turing machine which is able to simulate all other Turing machines. It sounds very abstract, but practically that is a concept of a general purpose computer, like your laptops, like our smartphones. That only means that a finite number of other programs can operate on your machinery. Now, this is the concept of digital computing. And later on, that was technically realized by Konrad Zuse in Germany, by the way, the first, 1941. It was a pity that that was in the time of the war, and the Americans did not realize that, and they believed, oh, we were the first with John von Neumann, but John von Neumann was 45. People who are interested can have a look on the Zuse, first Zuse machine here in Munich in the Deutsches Museum. Now we want to consider the philosophical background. The philosophical background is the following. The idea of the quantum computer historically came up in 1982, and it was suggested by Richard Feynman, famous American Nobel Prize winner. And what did he suggested in this famous paper, Stimulating Physics with Computer? His argument was, obviously, The universe is a quantum universe. Quantum physics is the fundamental physics of the whole universe. Classical physics is only an approximation in a certain kind of scaling. Then this argument was, if we want in physics to calculate this world, we are still using classical machineries, like the digital computer a la Turing and the von Neumann machine, classical machines. The better way would be to have a quantum computer in order to simulate what is going on in the world. And that was the birth of the idea of the quantum computer exactly in that year. This is Konrad Zuse. I mentioned him already. And Konrad Zuse, before Richard Feynman, had already the idea, but now in classical physics. Let us consider the universe in the sense of classical physics. And then we have the classical computer in order to simulate what is going on. So his idea was, let us consider the classical world as a digital world. As a digital world, and all these states in physics can be reduced to the digits. Practically, that is done in physics, of course, as approximation. It is done as approximation because we use digital approximation to classical physics to approximate classical states. And that is done everywhere nowadays with the modern digital computer technology. And only some guys here in Garching and elsewhere, they are interested now in the quantum computer. So that is, on the one side, a very philosophical idea of Zuse, namely, let us consider the world in the sense of a digital world. And on the other side, simulating it by classical computers. In a special version of the classical computer, he suggested were the cellular automata. That means, in the end, equivalent to a Turing machine, equivalent and simulated, it can be simulated on a classical computer, a world which is built up with units, and the change of the units, digital, is realized by cells. That means, let us imagine that the whole world is built up by simple, very elementary building blocks, and they represented the states of the digits, black and white, 0 and 1, the digital world. That is the idea, was the idea of Konrad Zuse before Richard Feynman came up with the argument, no, the world is not classical, it is a quantum world, and therefore we need a quantum computer. 1985, a British logician and mathematician came up with the idea, the quantum computer. The quantum computer is a generalization of a Turing machine. In the end, it is a Turing machine. So he suggested a universal quantum Turing machine and extended, Church sees this now, for a quantum Turing machine. That was the theoretical, let me say, the philosophical concept. And now, that is maybe a little bit ambitious now. Let us consider what is going on in quantum computing from a logical epistemic point of view. Perhaps you know, in informatics and computer science, we have a theory which is called complexity theory. And that means, practically, we distinguish problems with relation to the computational time which is needed to solve these problems. And I only want to highlight one main difference, which is made in this complexity theory, namely the difference between the so-called P and NP problems. P problems means these are problems which can be solved in a polynomial time. Polynomial time means the time function is mathematically a simple polynomial. And that means in the end, for us here now, it can be realized in practical time, in our lifetime, by, that is now crucial, by a deterministic Turing machine. That means a concept which was at first introduced by Turing, 36, 37. And these are a lot of everyday problems which here belong to this class of problems. But now NP problems. NP means, in the abbreviation, in the strict definition, these are problems which can be solved in a polynomial time, practically, but by, therefore n, by a non-deterministic Turing machine. And that means, in the end, this problem may need exponential time. So NP problem means practically these are problems which cannot be solved with our technology nowadays. As you perhaps know, it is an open problem until today. If for these NP problems, in the end, there may be a P problem solution. That is still theoretically open. But anyway, practically, it seems to be these are the real world problems which can be solved, and there are problems very, very difficult. NP complete, by the way, means that this kind of problems are equivalent with all kind of NP problems. And these are the very hard problems nowadays to solve. Anyway, let us consider a concrete example of an NP problem as far as we know today. It is a problem of encoding. In a simple way, you can imagine there is a message, and the message is divided into parts, and each part is represented by a number. And then we can multiply this number, we get another number, and this is the code of the whole message. That is simple. That can be done in a P way by a polynomial time computer, but vice versa. If you have a code, and of course, therefore, this kind of encoding is used nowadays practically. If you have a code, then it is very, very ambitious to find the factors representing the parts of the message, vice versa. And that is a so-called factorization problem. Now, the point was that in the end of the 90s, a computer scientist, Shaw, could prove if we have a quantum machine, and if we can realize technical and quantum algorithm, that means a combination of quantum gates, then it is possible, and he proved that theoretically in the end of the 90s already, then this factorization problem can be realized in practical polynomial time. So what was he doing? He was shifting the practical limit of NP problems to the practical limit of a P problem. But these are practical limits, which are here changed by quantum computers. So the point is, and that is especially shown by Deutsch and others, it does not concern the principle, the logical limits, which are integrated with digital computing. And they are already founded in the concept of the Turing machine itself. And that was a famous problem which was highlighted by Turing himself, 36, 37, such a principal limit of digital computing, the so-called halting problem or stopping problem. That means the question, is it decidable for any kind of Turing machine? Is there a universal algorithm to decide for any Turing machine, for any input of the Turing machine, whether the Turing machine will stop or not? What practical means, stopping means there is a solution of my problem. And that can be shown to be, by logical reasons, in principle, not decidable. And this kind of problems are not concerned by the quantum computer. Quantum computer is very nice, but it only concerns practical limits, which were illustrated here by the example of Shor's algorithms. By the way, it is not excluded that some clever mathematician or computer scientist will come up tomorrow or now with a solution, with a classical solution of Shor's problem. That means someone who find a classical algorithm to do that very nicely on the Leibniz machine in Garching. So I want to highlight that to give you a feeling between, and that is an epistemical question, between practical limits, and they concerns quantum computing, and principle, logical limits. And these limits are not concerned. Now, in the end of this part, let me come again to the vision of Feynman and of Konrad Zuse, namely the digital world. This is another Alice, not our Alice in quantum computing, in quantum communication. This is Alice in the Wonderland. And what is she doing? She is looking behind the curtain of the phenomena. And what does she see? Digits, bits, quantum bits. And that was highlighted by the teacher of Richard Feynman, this famous American Nobel Prize winner, which I mentioned several times, in a very nice formulation. The question, it from bit, what does that mean? It, philosophical speaking, all kind of being in the world. Is it in the end reducible to our bits? That was the vision of Konrad Zuse. That means in the end based by digital physics. And actually the practice nowadays in physics is all calculations are done on the computer. And it seems to be that all kind of information of the world is reduced to bits. Only in the theory we are thinking of real numbers as infinite entities, but in the praxis all is finite on the computer. And therefore it from bit, or in the quantum world with his famous student Richard Feynman, it from quantum bit. And that leads in the end, that's now my last slide in this part, leads to the question, is physics in the end based on information, or is information based on physics? That is illustrated here. That was the usual way which were used by me to introduce quantum communication, quantum information. That means we start with physics, material entities, the elementary particles. The elementary particles are described by quantum states, and then the quantum states were interpreted as quantum bits, and the quantum bits are the building blocks of information. So in that way, information was derived from physics. But the other way is nowadays also possible. We start with information. We start with concepts of information, of quantum information, quantum bits. We build up all our information in this way, and then, vice versa, we say, oh, there's a quantum bit, and we can interpret the quantum bit as a quantum state. And the quantum state may be the state of some entity, some system, and we call them particles. And then with the particles, we go on and build up the whole physical world. That is here. Fundamental is information, and then physics is divided. That means in the information theoretical interpretation, quantum theories are no theories about the properties of material objects, but about the representation and manipulation of information. That was in detail, by the way, done by famous authors. I will not go here in the details. That is not only now a philosophical interpretation, but that can be elaborated in all details. I have not the time to do that. In the end, that leads us to our philosophical sources. You remember that was my plea in these talks. In its fundamental basis, modern physics is philosophical. Philosophy is not an add-on. The basis is philosophical. So that leads us to a fundamental question in the beginning of science and philosophy. The one position is Plato. Plato, for him, the ideas, the mind is fundamental. And from that, all kinds of entities are derived. But the other position, pre-Socratic, great natural philosopher, physicist, they called themselves physicists, was Democrat. In the beginning is matter, in the beginning are the atoms. And all is derived, all phenomena are derived by combinations of the atoms. That was his great idea. It seems to be that modern science is more or less following his strategy, but the other strategy is in principle also possible. I will not decide this question here. It's only food to think for you. And with that remark, I conclude this part. Thank you for your attention.